So, assignment six, that's due um, on the 21st. That's on Wednesday, and then the final exam. That's Wednesday the 28th. So the week after that, from 12:30 to 2:30 on chapter 6 and 7. Um, so that one's 2 hours long. So it's a little bit longer. Although I won't, make the exam longer than that. Than it needs to be. And we should finish up chapter 6 today or next time. All right. Questions on the sixth assignment?
This isn't on the sixth assignment, but when will assignment 7 be due?
Oh, the day, I think the day before the exam. So assignment 7. Uh, so we'll say Tuesday. So that's 4/27.
But will we get those back so we can look over them and stuff?
Oh boy, I'm not sure I can do it that quickly. I will post solutions, of course, and I'll do my best to get it back to you.
I see. All right. Thank you.
Okay. But given the compressed timeline a little bit here with that assignment, I would not wait. I would not wait to start it. Need to be started right away as soon as I post it, and we'll say I'll post it this afternoon. So. Okay. So questions on number 6. Let me pull it up here.
On number 2, in the inductive step,
Uh-huh.
when I'm in the string of inequalities, trying to, substitute stuff in, I get to, n squared plus 2n plus 1 is greater than 2n plus 3 plus 2n plus 1 by the
Right.
inductive hypothesis. But beyond that, I'm stuck.
Sure. Yeah, there's a little bit of, like extra kind of creativity that goes into that step. So we're trying to show, so this is on number 2. So you're trying to show, so you assume n squared is greater than, what is it, 2n plus 3 for some n, what is it, n bigger than or equal to 4. All right, and you want to show that n plus 1 squared is greater than, and then what's this become when you plug in n plus 1 for n?
2n plus 5.
2n plus 5. It's true as well. All right, well, so, n plus 1 squared is equal to n squared plus 2n plus 1 is greater than, and then the n squared is bigger than 2n plus 3 plus 2n plus 5. Or 2n plus 1, sorry.
Yeah, that's where I'm stuck.
Fine. All right, you only need that this is bigger than 2n plus 5. All right, so what's the smallest? And you have to use the fact that n is bigger than or equal to 4. You don't have you don't want to add the 2n and 2n. You don't want to say that this is equal to 4n. Right? I mean, one could say this is equal to 4n plus 4. But I wouldn't go that direction. Although someone sent me like a preliminary draft, and they did go in that direction, and actually it worked out fine. But I think this is maybe a little bit more immediate. Right? You've already got the 2n right there. Right? So, and all you want is that, this sum is bigger than 2n plus 5. It's not a high bar to cross. What's the smallest this could be? When n is at least 4. It's a line. What's the smallest value a line takes? On a given interval. Right? The smallest value in that interval. So what's the smallest number that this could be?
11.
11. All right, well, there you go. Yeah. I mean, you don't even need that much. You don't need 11. All you need is 4. Because you already have a plus 1, so all you need is 4 more. Does that help?
Yeah, I think I see where you're going with it. Yeah.
Okay. All right. What else, guys? Let's continue with our discussion of the second principle of induction so that we can get to number 4 here. So remember the second principle of induction. To show that for all n, p of n is true over the domain D equal to 1, 2, 3, 4, 5, 6, 7, so on and so forth like that, or some other domain with the smallest of consecutive integers with the smallest starting point, it suffices to show the following. P1 is true, that's the base case. And now the inductive step is a little different. Not that Pn implies Pn plus 1, but P1 and P2 and P3 and P4 and all the way up to Pn, that all of those together imply Pn plus 1. Now this is actually logically equivalent to the first principle of mathematical induction, although we're not really getting into why. But the second principle of in the first principle of mathematical induction, step n plus 1 follows from step n. In the second principle of induction, step n plus 1 need not follow from step n. It follows from some previous step or some previous steps. And examples that actually need the second principle of induction are actually a little hard to come by. So the examples are trickier. They're a little harder to come by from an introductory, standpoint. Once you've started in on graph theory and understand graph theory to a certain extent, or certain types of discrete geometry, then there's lots of examples. But if you don't have that jargon, we can't really do them. But here's the first example but I've got more examples than most people will give you, just to let you know. The second principle of induction, the standard example is this, and it's a very good one. For every integer n bigger than or equal to 2, that integer is either a prime or a product of primes. So either prime or a product of primes. Well, a prime by itself you can consider to be a product of primes, but say it however you want. So, for example, 100 is equal to 25 times 4. So the fact that 100 is a product of primes follows not from the fact that 99 is a product of primes. It follows from the fact that, like, 25 and 4 are both products of primes. Or from the fact that 50 and 2 are both products of primes. Right? That 99 is a product of primes. 99 is 9 times 11. 9 is 3 times 3, and 11 is prime. So this gives you that 99 is 3 times 3 times 11. That has nothing to do with the fact that 100 is equal to 2 times 2 times 5 times 5. Don't even use the same primes. Right? So this is a great example. And here's how it looks. And the tricky part in such a proof is, how do you write the induction hypothesis? Okay. So assume base case is 2. And 2 itself is a prime. Just in case you were confused about it, 2 is a prime. It fits the definition. 2 is a number that is only divisible by itself and 1. Okay, but the number isn't 1 itself. Okay, so 1 is excluded from being prime. Why is 2 a prime? Well, it makes this theorem work. If you exclude 2 from being a prime, well, suddenly 100 is no longer a product of primes. So it's the quote-unquote right choice to make 2 a prime. All right. So the inductive step. So we're trying to show that P2 and P3 and P4 and Pn minus 2, Pn minus 1, Pn, that all of those together imply Pn plus 1. So you have to write down the induction hypothesis and introduce a new variable aside from n. So for every k in the range from 2 to n, right? So we've proven the base case at 2, and then we assume it's true up to some n. So for every k in the range from 2 to n, k is prime or a product of primes. Okay. Now show that n plus 1 is prime or a product of primes. Well, if n plus 1 is itself prime, then you're done. So assume n plus 1 is not a prime. If n plus 1 is not a prime, then n plus 1 is equal to a times b. And the key observation is, when n plus 1 is equal to a product of two smaller numbers, those smaller numbers are between 2 and n. They must be less than n plus 1 and greater than 1. So a and b both fall in the range from 2 to n. Less than n plus 1, bigger than 1. So by the induction hypothesis, a and b in this range, everything in that range, k in that range, is prime or a product of primes. So a is P1 to PS as a product, P1 times P2 up to PS. B is Q1, Q2 all the way up to QT. I shouldn't have a comma there. It's a multiplication. Q1 times Q2 all the way up to QT. It could be that S or T is 1, so that one of them is prime or whatnot. But each PI and each QJ, they're each prime. Okay, so now n plus 1, which is equal to a times b, is the product of the p's and the q's, which is therefore a product of primes. And that's the proof. Here's another really good example. Strictly speaking, it doesn't really need the second principle of induction, but I think it is more natural with the second principle. So prove that the sum of the measures of the interior angles of an n-sided polygon. Does anyone know what it is? Is what? Well, y'all know what it is for a triangle. It's 180, right? So in general, it's n minus 2 times 180 degrees. All right, so like, for example, Oh, for all n bigger than or equal to 3. If it's less than 3, of course, it's not actually a polygon. So for example, like, triangle, the sum of those angles is 180. All right, 180 degrees. For a four-sided one, any four-sided one, the sum of those angles is 360 degrees, so on and so forth. All right. So this is one example where the base case is non-trivial. So before we get into the proof, let's remember something. Remember, 360 degrees is the angle swept out by the radius of a circle, right? Right. Therefore, 180 degrees, right, so this is some radius. 180 degrees is what? The angle swept out by half a circle, i.e. a straight line. That is the angle of a straight line. Right. All right, so let's start with the proof of that statement. So the base case is n equal to 3. So we have to prove that the sum of the angles of a triangle is 180 degrees. That is, the angles together form the angles of a straight line. Not the angles, the angle of a straight line. Right? Does anybody know how this proof goes? Anybody? You seen it before? Anybody? So we'll call this angle alpha, we'll call that angle beta, and call this angle gamma. All right, so now what you want to do is take the bottom line here and extend it and put a parallel copy up top. Not a straight line. Can you have a line tool in this thing? Yeah, I do. Use that. Alright, so we take a triangle. And we've got those three angles, alpha, beta, gamma. And now extend the bottom line, any line, doesn't have to be the bottom one, okay, into a longer line. So extend one side and copy it to the opposite vertex as well. As shown. So I'm going to take this I'm going to take that bottom side, put it over here, and we're going to extend it. And we're also going to extend the bottom side itself. All right. So now we have two parallel lines cut by several transversals. Two different transversals. Therefore, we can fill in the angles missing angles as shown. So the whole proof of this rests on this thing about, opposite interior angles of two parallel lines cut by a transversal are the same. So one actually has to, establish that fact somehow. But assuming that fact, we have what we want here. So, right, here's a transversal. So this angle right here is what? So here's a transversal. This angle is gamma, so this angle is gamma. Here's a transversal right here. This angle is alpha, so that angle is alpha. So alpha, beta, and gamma stack together to form the angles for a straight line. So their sum is 180. Alpha plus beta plus gamma makes a line. So alpha plus beta plus gamma is 180. Yeah. So this is a nice example because it uses a second principle, and also because the base case is non-trivial. This is like, I think, one of the only ones we're going to do in which the base case is non-trivial. Not that they don't exist. There's certainly plenty of them. All right. So now the induction step. So the induction step is that P3 and P4 and Pn implies Pn plus 1. Now, actually, there is a proof that Pn implies Pn plus 1, but this is much nicer, and it uses the second principle of induction. So what's our assumption? Assume that for what? You got to introduce that second variable. Assume what? For every k in the set from 3 to n, that the sum of the angles of a k-sided polygon is k minus 2 times 180. Okay, degrees. So in order to write the induction hypothesis properly, you need to introduce this second variable. unless you're going to say it very carefully without doing that. I would actually do it this way. Assume for every k less than or equal to n, assume for every polygon with at most n sides, people might say. But let's not get too fancy. Let's do it this way. That's implying a second variable. You're just not giving it a name. So you need to introduce a second variable. So n is your unknown that you're working with. So now we introduce k or l or s or t, whatever you like, to represent the range from the base to n. So for every k in the range from the base to n, pk holds. So now show that the sum of the angles of an n plus 1 sided polygon is what? All right, pk is k minus 2 times 180. So pk plus 1 or pn plus 1, put in n plus 1 for k and you get what? What's the expression going to be? It's not n minus 2, right? What is it?
N minus 1.
N minus 1. N plus 1 minus 2, which is n minus 1, is n minus 1 times 180 degrees. Okay, so take a polygon P, having n plus 1 sides. Draw a line. Well, let me draw it. So a picture is sometimes useful to sort of illustrate what you're doing. The picture isn't the proof, but it can help sort of with explaining where you're going with things. So here's a polygon, P. Okay, take two vertices of P and join them by a line that is interior to P. Of P by a line in the interior of P. Move this down. On the next page. Or no, I can put it down here. Therefore, splitting P into two smaller polygons, P1 and P2. So let's make it red. So here it is. So we've got this line here, and now we've got two smaller polygons, P1 and P2. All right, P has n plus 1 sides. By assumption. P has n plus 1 sides, and say that P1 has A sides and P2 has B sides. Therefore, A plus B is equal to what? So, P1 has A sides. P2 has B sides. P1 sides, what color are they? Well, all of them are black, except for the red one. One of them's red. And P2 has B sides, all of them being black except for one, which is red. P, its sides are all black. The red one isn't there. So if I add the length of A, and the length B together, I get P plus how much overcount? How much did I overcount the sides of P? Right? P has n plus 1 sides, but twice, right? So it's n plus 1 plus 2 equals n plus 3. Since A and B are at least 3, we get that, right? A and B are, so each of A and B is at least 3, as small as 3. So how large can they be? Right, so like if A is 3, then how big is B? A plus B equals n plus 3. So if A is 3, how big is B? Hello?
N plus 1 plus 2.
No, suppose B is 3. Suppose B is equal to 3. Then what's A equal to?
Just N.
The n, right? So that's as large as A can be. So A and B, they're both as small as 3 and as large as n.
Oh, I see where you're going now.
So what can we say about P1 and P2? What did we assume about such polygons? Oh, why does it do that?
Well, now it's not there.
It gives us nothing. We lost our assumption. So what do we get about polygons with k sides for k between 3 and n?
The sum of their angles is k minus 2 times 180.
Yeah. So by the induction hypothesis, actually, no. You can't use the first principle. It does not follow from the first principle. Well, that's interesting. I always thought it did. But technically, not really. Unless you're assuming ahead of time that you know the fact that a triangle has angles summing to 180. Anyway, so by the induction hypothesis, the angles of P1 sum to A minus 2 times 180 degrees. And the angles of P2 sum to B minus 2 times 180 degrees. Now, notice that the angles of P is simply the angles of P1 plus the angles of P2. So I'm going to make the angles of P1 blue. So blue angle for P1. And I'm going to make the angles for P2 green. Right, so every angle of P is either a blue angle or a green angle or a sum of a blue and a green. Right? A minus 2 are blue ones, B minus 2 are green ones, and two of them are the sum of one blue and one green. So notice that the sum of the angles, let me write it, the sum of the angles of P is the sum of the angles of P1 plus the sum of the angles of P2. The sum of the angles of P is the sum of the angles of P1 plus the sum of the angles of P2. And we know what those angles are, those angle sums are. They're A minus 2 times 180 plus B minus 2 times 180. So, therefore, is A minus 2 times 180 degrees plus B minus 2 times 180 degrees, which is equal to A plus B minus 4 times 180 degrees. What was A plus B equal to? Remember, we wrote it up top.
N plus 3.
N plus 3. Which is equal to n minus 1 times 180. And that's what we wanted, right? That's what we were looking for. It's up here. Show that the sum of the angles of an n plus 1 sided polygon is n minus 1 times 180. And that's what we got. So that's a neat formula. Yeah, I retract my earlier statement. You can't prove it using the first principle. It must be done using the second. Unless you're going to take the base case as assumed outside of the statement itself, which I guess is kind of cheating, but yeah, anyway, technicalities. All right. Third example, I guess this will be all for today. Oh, no, I wanted that. So notice number 4. So number 4 is our statement on the homework problem that's going to be done by the second principle. The other 3 are done by the first principle. So use the second principle of mathematical induction to prove that every propositional logic statement is logically equivalent to a propositional logic statement that uses no connectors other than or and not. So no implies, no ands, no implies, no ands, no if and only ifs, just or and not. So I can rewrite the statement in some other fashion using just ors and nots. So I'm going to do one like almost exactly like this, but I'm going to do implies and not. Okay? I'm going to do implies and not. All right. So let's prove that every propositional logic statement is equivalent to another propositional logic statement which only uses the connectors implies and not. All right. So the proof will be by induction on the number of connectors in the statement. Be by induction on the number of logical connectors in the statement. So before we get into that, let's talk about notation just a little bit. So for example, for example, all right, let's say A is a statement. Statement, no connectors. A, B, C, D are atomic statements. There's no connectors in them. It's like, you know, A is apples are sour, B is, you know, bats fly, C is cats meow, and D is dogs go wolf or something, okay? So no connectors in there. Okay, so now here's a statement with one connector. So something like A or B. Right, C and D. Right, A implies D. Those are all one connector. Here's two connectors. A or B not. C not and D. A not implies D. So the not counts, or A and B implies D. Right? These are all two connector statements. A and B or C, two connector statement, etc., etc. Okay, so the not counts as a connector. Now, when we say that P is a propositional logic statement with n plus 1 connectors. And now say that P is equal to Q implies R, where implies is the final connector. There's always a final connector. Right? Some connectors come before others, and there's always going to be a last one. Sometimes you may have a choice as to which is the last one, like with you know, a bunch of conjugations, like, but in this one, you know, these are the last connector. Well, no need to color them differently. Here, this is the last connector. In this one, this is the last connector. And in this one, this is the last connector. And in this statement, these statements here, the last connector in this one is the or, the last connector in this one, by operator precedence, is the implies. Whatever the case might be. Okay, so now say P is a propositional logic statement, and it's got lots of ands and ors and implies in it. It's a big old compound propositional statement. Dogs go woof and cats go meow. Therefore, mammals make some kind of noise, and, you know, if a tree falls in the forest, then nobody hears it, and nobody hears it, then it didn't make a sound or whatever. You know, I mean, it's a big old statement, but it's propositional logic. Okay, so now suppose that the last connector in P is implies. Therefore, P is equal to Q times R, where Q and R together have to have connectors. Where Q has A connectors and R has B connectors, therefore what? A plus B is equal to what? So P has N plus 1 connectors. Here's the last one. How many are left over? All right, so P has 20 connectors. Here's connector 20. How many are left over?
Just that one.
Nope. P has 20. N, right, in this case, N. P has N plus 1 connectors. Here's the last one. There's N left. So A of them are in Q and B of them are in R, where A or B could be 0. So A plus B is equal to what? Not N plus 1, but what? Look here. This statement has 2 connectors. Here's the last one. So here's the 2 statements left over. How many connectors are here? 0. How many connectors are here? 1. 1 plus 0, is it 2? No, it's just 1. So A plus B is equal to
N.
yes. Okay, so we want to now go to the proof. Now let's take a look. Use no connectors other than only the connectors. It's fine. We want to prove that every propositional logic statement is equivalent to another propositional logic statement which uses only connectors, implies, and nots, or no connectors at all. You know, no connectors at all would be fine. So the base case is n equal to 0. So a propositional logic statement uses, with 0 connectors, doesn't use connectors other than implies and not. So there's nothing to prove. Okay, induction step. So the induction step, So here the base case is 0. P0 and P1 and Pn implies Pn plus 1. So assume that any propositional logic statement with K, which is an element of 0 to n, connectors can be written equivalently using no connectors other than implies and not. Show that a propositional logic statement with n plus 1 connectors can be rewritten using only the implies and nots, or nothing at all. Nothing at all counts. Alright, so say that P has n plus 1 connectors. Therefore, either P equals A or B, P equals A and B, I don't think we're going to be able to finish this today, but P equals A or B, P equals A and B, P equals A implies B, not logically equivalent to, is actually equal to. P equals A if and only if B, or P equals A not, where A, capital A, has little a connectors, and capital B has little b connectors. Since P has n plus 1 connectors, A plus B is equal to n, not n plus 1, because the last connector is either or, and implies if and only if, or not. So by the induction hypothesis, because so A plus B is equal to n. In particular, A and B are both less than or equal to n. So by the induction hypothesis, right, A is logically equivalent to Q, where Q uses only implies and not. And B is logically equivalent to R, where R uses only, implies, and not. Okay, and then finish this from here. Okay, we'll do it on Monday, but take a look at this and try to understand what's going on. Okay, or I'll write it out. You guys can go now. I'll write it out, but please take a look at that over the weekend while you're doing your homework for this, and come with some questions. Okay. All right, guys. Have a great weekend, and I'll get the exams to you, sometime this weekend. All right. Okay.